All right, so now you understand the different phenomena that occur with different wavelengths or different energies of photons and how they interact with matter. And so absorption of light can take on many different forms, right? We can have absorption of light that synchronizes with an electronic excitation in energy levels or orbital energy levels in a molecule. We could have infrared light absorption, which excites different vibrational modes, or microwave light excitation, which excites different rotational modes, etc., etc. But how do we actually measure the absorption of photons? The simplest way, at least for ultraviolet and visible wavelengths of the spectrum, we're going to use this thing called a spectrophotometer. And you've all used one. You've all used this Spec 20 or Spec 21 or whichever model we have in the chemistry department when you were in general chemistry. And the way that those things work is you have your black body source. In this case, this is just an incandescent bulb, and that's heated up. So that's how a light bulb works. Literally, an old incandescent, usually you just have a really thin tungsten wire. That thin tungsten wire it's coiled up like that, so it creates a high resistance. When you have current being forced through that thin wire, it undergoes this process called ohmic heating. This thing is evacuated, meaning it's under vacuum, and there's no oxygen inside of that bulb, which would cause this to turn into tungsten oxide. So it can just glow and be tungsten, and the actual wavelength centroid of the power spectral density here is a function of its temperature. So that's how we get the light, and then we call this broadband radiation or white light. Sometimes it goes through a collimator or some sort of lens to take the light and not focus it, but take the rays, which are sort of in no particular order, being emitted what we call isotropically, where they're being emitted from the tungsten filament in all possible directions. And it takes that and it makes it a parallel set of rays. Then we run that through a monochromator. A monochromator, as the name implies, is this thing that yields a single wavelength. And there's a variety of different monochromators. We're going to talk about that a little bit later in a subsequent video when we talk about the physical pieces or components. But you can think of a monochromator, the simplest version of that would be like a prism. And you've all seen a prism, you know, if you hang one of these chunks of cut glass in like your window, which I have right above the camera here, what you'll see is white light from the black body source, which is the sun, coming in, and that light gets dispersed, which means that actually different wavelengths of light travel at different rates through that refractive medium, meaning that it has a refractive index that's not vacuum. And so because they bend sort of differently because of their different rates of or velocities in that refractive medium, you get this dispersion effect. And that's how we split white light into its component light. And then what's key to, at least in a prism, what's key to selecting that particular light once you've dispersed it is then to have some wavelength selector, which is the slit here. And so we can move this position here up and down, which allows us to select for particular bands of light, different wavelengths, or we can move the prism here and rotate that in space. Either way, those are both possible configurations of simple spectrometers. Then we have our solution. Right, so this whole front end is just the light, and really the main goal here is to take broadband light of all different colors, at least in the visible and the UV, and then control which one we're sending through. So we know what wavelength we're sending through at any given moment in time as it exits the slit. Then it passes through our sample, which there's a variety of different sample holders. You're used to using a cuvette, which is this sometimes it can be a cylinder, but most often it's this rectangular shape that's made of some material that's not going to absorb the radiation that you're trying to put through it. So if you're using visible light, then glass is fine. Even acrylic plastic is fine. If you're using UV actually is absorbed by glass. That's why you don't get a sunburn while you're in a car. As long as the windows are up, is because most of the UV is absorbed by the glass itself, in which case you have to use quartz, which is also glass, but it's crystalline glass rather than amorphous or a disordered glass in terms of its structural components. More on that later. So the sample passes through the cuvette, and there's two different measurements we take here. We measure one without our analyte in solution, which would be what we call the blank sample. The blank sample is where we measure all of the intensity of the light because any amount of light that gets refracted or absorbed by the glass or anything in the system, that's taken into account in this measurement because we say that there's zero analyte concentration in the system. So we'll say that whatever x is equal to 0 for the blank measurement. And then we have our actual sample as the second measurement, which we call, I don't know what this particular cartoon that I got off of the internet says, but normally we just call that I. That's the intensity. And that's when the sample concentration, the analyte concentration, is greater than 0. So when we're thinking about how much light was measured, we measure that in two different ways. We measure it either with this metric called absorbance, which we'll talk about in a second, but easier to conceptualize is this metric called transmission or transmittance. And if you recall, most analog displays, like what you have used in Gen Chem class, they actually have a scale where the scale looks like this, and you have percent transmittance on one axis and you have absorbance on the other. And the needle reads both simultaneously because they're functionally related to each other, as I'll say in a second. So the transmittance here is going to be the intensity of our light here as it passes through the sample. So this is some value where some amount of the light has been lost because it's absorbed by the sample, then divided by whatever the intensity is of all the light passing through. And so this number is always going to be larger, presumably, than this one. And so what we end up is a fraction of the overall light that passes through, which tells us how much actually gets through. What's the percent transmittance of our sample. So we can multiply that by 100, and that gives us this thing called percent T. So percent T is nice and handy. We also measure in using this metric called absorbance. Absorbance is actually logarithmically related, so we call that negative log of T. And here T is not percent T, it's the original T, so we could write this as negative log I over I naught. Or absorbance could be just the log of I naught over I, which you'll sometimes see too, just the negative inverting the quotient here. So let's think about what these values mean. When you have all of the light passing through, so it's actually the same as all the light from your blank, meaning I is equal to I naught, then our percent transmittance is 100%. And that makes sense, right? Because it means that whatever light passes through without the analyte is the same as the light with the analyte, meaning there's no analyte, or there's no, the analyte's not absorbing any light in this case, and so we get 100% transmittance. If we take the negative log of 0.1, we get an absorbance of 0, which should make sense, because if you have 100% transmittance of light, then there's no absorbance by your analyte itself. So let's think about if you have, say, 10% of the light that passes through, which would be 0.1 in terms of the intensity over intensity naught, or the intensity of the blank. What is the absorbance of 0.1? Well, that's an absorbance of 1. Which is quite high. If you've remembered measuring the absorbance before, we often will make assertions about what a reasonable absorbance of your analyte is, and the reason is because of this. Let's take this one step further. So if we only allow, or if our sample only allows 1% of the total light to pass through, then imagine you've got all this light blasting through your instrument here, but only 1% of that signal is actually striking the detector. So that's not a very good measurement because you're actually not getting much signal hitting the detector. So negative log of 0.01 is an absorbance of 2. And so often, and you probably have heard this before if you've taken other courses that use absorbance a lot, especially if you take like biochem, and we often say for most spectrometers, we don't accept measurements in excess of 2. Some spectrometers, some modern spectrometer detectors can maybe get up to 3 in a reasonable way, which would account for 0.1% of the light. But imagine, right? You have this bright light, all this signal, and then you only have a trickle of it hitting your detector. You have to have a really incredible detector to be able to reasonably measure only 0.1% of all of the light and still do that in a linear way. So we often call the linear range of absorbance measured in a spectrophotometer, often typically 0 to 2, maybe 2.5, and then in some high-end research spectrometers up to 3. For cheap spectrometers, sometimes that absorbance range is linear only up to 1, especially at sort of the bounds of the UV and the visible spectrum. And this is because the fact that you're absorbing such a small fraction or you're actually transmitting such a small fraction, which is the signal you're measuring. So we know that at least for UV visible range of our spectrometer, that what's really happening inside the sample solution if an absorbance occurs is we have a photon of light, one of these that passes through after it's left our monochromator. If the photon of light in terms of nanometers or energies in joules, if that exactly matches one of the transitions for our electron, then that will excite an electron and we consider that photon absorbed. That's what's happening every time a photon of light gets absorbed. So of course when we have I significantly different than I naught in a blank, what we have are a whole bunch of molecules in that cuvette that are undergoing this transition, and we're absorbing those things. So it's important to remember, we're not going to fundamentally derive this relationship, but there is a relationship between how much of the sample is actually, or the analyte is dissolved in the solution, and the absorption, how much of the light gets absorbed. And of course, you can think about this intuitively. That will probably also depend on then how much of the light or how thick of a sample solution the light is passing through. Because if you extend this out and you make it doubly as wide, then of course you have more photons interacting with molecules. You would expect probabilistically you would absorb more photons. So we call that, and you've all used this before, we call this the Beer-Lambert law, which is absorbance is equal to this constant epsilon times what we call the path length times the concentration of the solution. You'll see this written in a million different ways. People like to call these variables all sorts of different things. I always learned it as epsilon LC. To me, it's the most intuitive use of variables. You'll see a lot of people, I don't know why, but they like to write this as absorbance is equal to ABC. And then they rename the variables as ABC. This is not that hard to remember for me, and it's much more intuitive in this way. So this epsilon here, we call this the molar absorptivity, is most common nowadays, but its epsilon comes from sort of an older name, which is the extinction coefficient. They're the same thing. This is essentially the constant of proportionality. So every equation has it, right? Every equation has some constant of proportionality that relates the key variable functionally and normalizes the units to some constant SI unit system. That's what molar absorptivity does. It's a constant of a particular molecule. I'll talk about that in a second. L is our path length. Path length is simply this. It's the width of the sample solution that the photons are passing through. And so you'll know that what sets apart a cuvette from a test tube, even though they look the same, is that the cuvette versus the cuvette is precision blown glassware. So L is known with at least 3 significant figures, which allows us to compute concentration with at least 3 significant figures in a spectrophotometric measurement. Test tubes are a dime a dozen, literally. They're really, really cheap, and so they're not precision machined, and so they may fit into your spectrophotometer. You may know different, but one tube to the next can be pretty significantly different in terms of its width, its path length, which leads to pretty significant error in the measurements that you're making. And then C, of course, is the concentration of the analyte. And again, this functional relationship between absorption and concentration typically holds on most hardware spectrophotometers in the region of 0 to 2 and sometimes up to 3 depending on the specific detector that you're using for a system. Since the absorbance is unitless, because it's simply a ratio or a log ratio of two intensities, there's no units affixed to it. So that means that the molar absorptivity has inverse units to the path length and the concentration. So concentration is normally measured in moles per liter or molarity. Path length is typically in centimeters. So that would give you centimeters times molarity, so molar absorptivity is most often measured in 1/meter centimeter or molar centimeters. You'll see this reported in different units, but this is the most common one, at least in the US.